Hello and welcome to this lecture. From this lecture on, we are going to start looking at power series, exponential and logarithm functions. Okay, so these are very crucial ideas. The exponential function, for instance, has tremendous applications in all of science and engineering, and there's a very good reason why it has this powerful application. And the theoretical basis for this exponential function is something called power series. And we'll also see logarithm, which is basically the inverse of the exponential. We saw these inverse functions, right? So you see inverse of the exponential is logarithm, and that also has a lot of applications in science and engineering. So let's go through and see this. We'll begin with an introduction. So here's a electronic circuits problem. Okay, so here's a capacitor discharging problem. It's a very classic problem in electronics. You have a capacitor which is already charged. It has some initial voltage across it. Okay, it is charged and it has some initial voltage across it. So Vc of 0 is not equal to 0. It is something positive. The value of the capacitance is 1 millifarad. And then there is a switch here, and the switch is open. So if it's open initially, no current is flowing and the capacitor charge holds, right? So that's what happens. So there is a 1 kilo ohm resistance here, and I'm throwing the switch here to close the circuit at t equals 0. So now current starts to flow, and you can write an equation very easily, right? So what is the value of the current? I of t. I of t is Vc of t divided by 1 kilo ohm, right? So it's all 1, but the units just change. Vc of t will be in volts. If you divide by 1 kilo ohm, you will get milliamperes, right? So I of t equals Vc of t divided by 1 kilo ohm. But adjusting the units suitably, I'll keep all Vc of t units in volts. I'll keep all I of t units in milliamps. So I simply get I of t equals Vc of t, right? So that's one equation. So you can see that. Another equation is, what is the current coming out of the capacitor, right? The same I of t is flowing in this direction out of the capacitor. So the current through a capacitor is C dV by dt, right? So C is just 1 millifarad times the derivative here, derivative of this. So Vc prime of t divided by, multiplied by 1, but that's the current in this direction, right? So this is I of t, so that will be the I of t is flowing in this other direction, so you will need a minus sign there. So looking at all of these things, solving the circuit carefully, I'll urge you to do it. I'm not going to do it in great detail. You see that this equation is satisfied by this circuit. Okay, so I of t equals Vc of t, and it's also equal to minus Vc prime of t. Okay, wonderful simple equation, right? You don't complain about units. There is a Vc of t divided by 1 kilo ohms here, and there's also multiplication by the farad and all that here. So it's okay. This is correct. I mean, I've just swallowed all these 1 inside, and I get this equation. So notice this equation. This equation is really interesting, isn't it? Vc, this function Vc of t, it is some function of time. Just like I of t is some function of time, Vc of t is some function of time. It has to vary with time. But interestingly, its derivative is the negative of itself. Okay. So curiously, we have so far actually not come up with any function which, when you differentiate, you get the same thing more or less, right? Okay, minus, except for that minus, you get the same function more or less. Okay. So this leads us to this very important question. If you have to solve a capacitor discharging circuit, okay, you need a function f which has this wonderful property. F prime has to be equal to plus or minus f. I've put plus f also. In this case, you got a situation like this. There are many cases where you will get plus f also. Okay. So this example is only one example where you need a function like this, f prime equals plus or minus f. There are so many examples all across engineering and science where such equations come. You want the derivative to be very similar to the function. Okay. So that comes because of the constraints in the system. Current is the derivative of the voltage. It's not isolated only for circuits. Even in mechanical systems, you have equivalents like this. You have the spring mass movement, right? The spring's energy is sort of like the derivative and all that. So you see velocity is the derivative of the position, and there are some things that respond to velocity. There are some things that respond to acceleration. So you have all these kind of equations even in mechanical systems. So you have these equations coming in there as well, and there also you need a formula, a function which has this kind of behavior. Okay, can we find a function like this? Okay, it turns out it's a little bit tricky. Okay, so if you were to look at a polynomial, okay, and ask a question, I have a degree n polynomial here. Can I have f prime equals f? If you try and ask this, you get very interesting answers. Notice what happens here. If I do a derivative, we will get a1, 2a2x, so on till n x power n minus 1. So there is possibility that up to degree n minus 1, you can make these two polynomials the same. but the nth term will differ, right? Between f of x and f prime of x for a polynomial, the nth term seems to differ. Okay, so let's check that. Okay, to make f prime close to f, we need a1 equals a0, and then you need a2 equals a1 by 2, right? 2a2 equals a1 or a2 equals a1 by 2. Now a1 is the same as a0, so I'll rewrite this as a0, and instead of just writing 2, I'll write 2 factorial. You'll see this factorial is important, you'll soon enough get something. Now a3 is going to be a2 by 3. Now a2 is a0 by 2 factorial. So if you divide by 3, 3 into 2 factorial is 3 factorial, you get a0 by 3 factorial. Okay. So likewise, you'll keep on going, you'll eventually end up with a case where an will be an minus 1 by n, and an minus 1 will be a0 by n minus 1 factorial. So you'll get a0 by n factorial. Okay. So if I enforce all these conditions, I get almost equality except for this nth term, this an x bar n is paining me, it's still there. Okay. So you can pick a0 to be 1, a0 can be any value, I'm just for convenience picking it to be 1. If you pick it to be 1, you see that f of x is 1 plus x squared by 2, so on till xn by n factorial. And this f prime is very, very tantalizingly similar to this f of x, except for this nth power term. Okay. So we saw this example earlier in the Taylor series approximation calculation. So you see that this polynomial is very interesting, as I keep increasing n, what happens? It starts becoming closer and closer and closer in some sense, right? In some sense, it seems to suggest that polynomials of this shape are very nice. But then if I stop anywhere, I'm in trouble. Because if I stop anywhere, my derivative is not going to be the same as the original polynomial. Okay. So a very natural question is, if stopping at n results in a problem, can I tend n to infinity? Okay. What is the meaning of tending n to infinity in a summation like this? Okay. There is some limit we have to take, right? What is that limit? How do you study it? All of this is the heart of this subject called power series. And when you have power series like this, you can solve problems like f prime equals f, and you can solve problems like discharging a capacitor. Okay. So solving power series, understanding power series, what these power series functions represent is crucial to all of engineering and science application. It's got wide, powerful applications all across engineering, and you should understand this connection very, very well. Okay. When you want good minute control over the function and its derivative, what is the connection between them? Then power series is your savior. Okay. So let's see a little bit of a starting point in this very first lecture. What is a series? Okay, we've seen series before, right? Good old definition. Go back to the initial lectures when we started series. First, we did sequences. Sequences are very easy. Sequence of real numbers ak, well, easy maybe. Okay, a0, a1, a2, etc. We know sequences. What we do for going towards series is we first consider partial sums. What are partial sums? I'm going to define them here. Sn is, notice this notation here, summation sigma k equals 0 to n ak. What this notation means is very, very simple. It just means a0 plus a1 plus a2. This sigma is like a plus. Okay. So I'm going to add all these guys together, and for every k, I'm going to put what value of k here I substitute, right? So sort of how we wrote the series expression, right? So these partial sums are like this. So S0 is only A0, right? N will be 0, so you will only have A0. S1 is A0 will be there, A1 will also be there, right? Summation k equals 0 to n, ak. So you will have S1 being equal to A0 plus A1. Likewise, S2 will be A0 plus A1 plus A2, so on, right? So this is how partial sums will behave. Now, the series is basically the limit as n tending to infinity of partial sums. Now, remember, partial sums is also a sequence. It's just Sn, just like ak was a sequence. Sn is a sequence in n, so you can put n equals 0, so you get S0, S1, S2 like this. This sequence of partial sums may converge, may not converge, whatever, right? But that limit is sort of referred to as a series. Okay, so the series has a lot of ways in which people write. This is the most common way in which you write. You have a sequence A0, A1, A2, so on, and the series is simply A0 plus A1 plus A2 plus dot 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 dot. Keep on adding everything, and up to infinity, you get a series. Okay, so crucial questions are: when does a series converge? What is the connection between the convergence of the sequence and convergence of the series? When can we say anything about this? So, because see the crucial nature, why you need to understand this, right? If you're going to solve discharging a capacitor, which is a very, very practical problem, you really need to know when such series converge, because only then you can use the, potentially you can find these functions whose derivatives are themselves. Okay, so it's very important to understand these things. Okay, so well, that's just one application. There are several applications to series. So series is a very powerful idea. Okay, so let me close this introductory lecture with defining the power series. What is power series? Again, you have a sequence of real numbers. I have a value x, which is a real value. Okay, so we're going to have a fixed number x here, and then consider this slightly different sequence. I'm going to take this a0, a1 and sort of try and make a polynomial series out of it, right? So that's what I'm trying to do here. So I have a0 and then I put a1x and I put a2x squared, and look at this sequence. This is still a sequence for me. See, remember, x is just a fixed value, so this is still a sequence. And instead of just having just a0, a1, a2 like that, I have a0, I have a1x, I have a2x squared, so on, right? Now I can make a series out of this sequence, and that comes from the sequence of partial sums, right? So partial sums, these are all, they're going to look like polynomials for me. This will be a0, a0 plus a1x, a0 plus a1x plus a2x squared, so on. Next you will have a cubic polynomial, fourth degree polynomial, like that. It will keep on going. So you will have this fn of x, which now becomes a sequence of polynomials. That is the partial sum sequence of this guy, right? And then I can look at the power series. This series of here, this guy of this fn, and n tends to infinity, is called the power series. Okay, so you see how this power series comes. You start with a sequence, and then you make this, bring in this x, and then you make these partial sums, and then you tend the n to infinity here, you get a series. Okay, so this is how a power series comes about. For any a0 and x, you can think of this power series. And just to show you a very concrete example, the power series that we considered earlier, if we don't stop anywhere, right, 1 plus x squared by 2 factorial, x cubed by 3 factorial, x power 4 by 4 factorial plus ... You don't stop anywhere. If you keep on going, you get something, right? What is this as a function of x? Is this interesting? Does it converge? Okay, these are the questions that we're going to ask. For what x does the power series converge? And how do you take derivatives here? You already have something converging here, and I'm going to think of this as some function x. Maybe this converges, but then how do you take the derivative? If you can crack these two problems, you've cracked the problem of finding a function f which is equal to f prime, right? If I can figure out the derivative, and if you can show the derivative is well behaved like before, you can just do term by term differentiation and add, then I'm done. I found a function, my magic function, which when differentiated results in itself, f prime equals f. Okay, and that's a very powerful function, and that function has tremendous applications in discharging capacitor. You'll see electrical circuits, it'll appear all the time. And as you study more of electronic circuits, the exponential function will be very crucial. It's also intimately connected to the sinusoidal and cosine functions, and so many connections from there. Okay, thank you very much.